Hi, I'm Professor Goins, and in this video I'm going to look at classifying the critical points using the second derivative. So if you remember, the critical points correspond to where the derivative is either 0 or undefined, meaning we have either a horizontal tangent line or a vertical tangent line. And in this diagram right here, we see that there is a horizontal tangent line at the very top and the very bottom, again corresponding to local maximums and local minimums. Now, how I'm going to use the second derivative is the following. If you look at the graph of this curve to the left and the right of that point, so let's just highlight a small portion of that graph, we can see that this is concave down. In other words, for the entire graph on the interval to the left and to the right of that critical point, that's concave down. So for every x value in between here, and remember what that means is if the function is concave down, the second derivative is negative. So that means that on that entire interval, for every x value in between there, the second derivative is negative. In particular, for the critical point. So the second derivative evaluated at the critical point, which I'll just abbreviate as CP, so the second derivative evaluated at the critical point would be a negative value. Similarly, if I look at this graph right here, this part of the graph here at this critical point, if I go a little bit to the left, a little bit to the right, and I highlight, say, this portion of the graph right here, then I see that that is concave up. What that means is for that portion of the graph, let's say corresponding to, suppose there, the second derivative is positive. In particular, the second derivative evaluated at the critical point is greater than 0. So we're going to use that concept to classify critical points as follows. We find the critical points, then I plug them into the second derivative. I evaluate the second derivative with those critical points, and all I have to do is look at is the value positive or negative. It doesn't matter if it's -1, -pi, -2 million. The quantity doesn't matter, it's just the sign, because the sign tells me about the curvature. Curvature tells me if it's a maximum or a minimum. So concave down, maximum, concave up, minimum, which comes from the derivative being, second derivative being respectively either negative or positive. So let's look at some examples of finding the critical point and then classifying them. So for example, find and classify all critical points. Okay, let's look at two possibilities, or two types of functions here. First, let's start with a cubic polynomial. So f of x is going to be x to the third minus 3x squared plus 4. And then part B, let's do an exponential function. So let's say f of x is e to the x squared minus 10x. So find and classify the critical points of those two functions. All right. First derivative for part A. So 3x squared minus 6x. Since that's a quadratic, I know it's never undefined, so I'm just going to take a look at when it's equal to 0, and we can factor a 3x out of that. So 3x times x minus 2 would give me the two critical points, 0 and 2. So to classify those, we have to plug these values in. We have to evaluate these using the second derivative. The second derivative in this case, so differentiating the first derivative would give me 6x minus 6. Substituting in the first critical point would give me negative 6, which again for emphasis is less than 0. And remember that the second derivative is negative, means that the graph, so second derivative negative means that it's concave down and that we have a local maximum. So this would be a x equal to 0 would be a local maximum. If I plug in the second critical point, so f double prime evaluated at 2, that would give you 6 times 2 minus 6, so 12 minus 6, which would be 6, which of course is positive. The second derivative is positive. That means, so second derivative positive on my diagram here shows me that the graph is concave up, and therefore I have a local minimum. So x equal to 2 is a local minimum. For the next example, again, I'll go back and I'll reference this diagram, so I'll erase what I have in the middle. So part B. Put the function up here again. We had e to the x squared minus 10x. Okay, so find the critical points. We start by computing the first derivative. So f prime. This is going to be a chain rule because I've got a composition with the exponential and the quadratic. So the derivative of the quadratic comes out front, so 2x minus 10. And then e to the x squared minus 10x. Again, linear is never undefined, exponential is never undefined, unless of course we had something as a composition here, but this is a quadratic, it's never undefined. So this whole thing is defined on the entire real line, so I don't have to worry about any undefined values. Exponentials can never be 0, so the only part of this that could be 0 is the linear factor, and we could set this equal to 0, add 10, divide by 2. We see that the critical point would be x is equal to 5. So now let's classify whether or not that's a local maximum or a minimum by computing the second derivative of this and then evaluating it with x is equal to 5. So for the second derivative, okay, so I've got a product rule, so 2 e to the x squared minus 10x plus the first factor here, which is 2x minus 10 times the derivative of the second, so I get an e to the x squared minus 10x. And then I'm going to get a 2x minus 10 using the chain rule, comes out as a factor, which means I'm going to have a 2x minus 10 squared. Okay, then I will plug in the critical point, so f double prime evaluated at 5. So that would give me 2e to the, let's see, that would be 25 minus 50 plus, I plug 5 in over here, I get 2 times 5, which is 10, 10 minus 10, which is 0, so that whole term is 0. And this is 25 minus 50. So this exponential, even if that's a negative exponent, this value is positive. So I've got 2 times a positive value, which is a positive value. And if the second derivative is positive, that means the graph is concave up, meaning I have a local minimum. And finally, we can say x equal to 5 is a local min. So again, that's how you classify critical points as local maximums or minimums, by simply evaluating the second derivative and remembering which way the concavity goes. Okay? Negative concavity is it's curving downwards, positive concavity is it's curving